Any questions from the previous lecture? Any feedback? So let me share my screen. Maybe we can wait for a couple of minutes and then we can start. There are around 30 participants at the moment. And then we have a chat. Yes, Manur, the tutorials will be uploaded on YouTube as well. But today is not a tutorial. Today is a class. Today we will cover new material. Start करते हैं जी. Bismillahirrahmanirrahim. In the last lecture, we talked about a very quick overview of machine learning. What do you mean by learning? What do you mean by machine learning? And then we talked about supervised learning, unsupervised learning, semi-supervised learning, a bird's eye view. That was our first glimpse of these concepts, these terminologies we use in machine learning. I hope there are no questions from the previous session. But I again want to emphasize a couple of concepts from the previous lecture. Right? So this is what I'm showing here is a quick, what is machine learning? So in the last lecture, I talked about what do we mean by algorithm and what do we mean by model. Anyone who can just recall what's the difference between algorithm and model? Maybe I can ask someone. Razi. What's the difference between algorithm and model? Yeah, algorithm fits data to a model. Right. Thank you, Asim. An algorithm in machine learning is a procedure, is a method that run on the data to create a machine learning model. A model could be a simple linear model, or it could be a quadratic model, it can be a decision tree, it can be a neural network. Right? So these are all different models. So learning the weights of these models using algorithm. So you can use different algorithms to fit data to the model. Right? So, for example, if you have a linear model, the number of weights. So these are called the hyperparameters of the model. And when you learn those weights, number of parameters is an hyperparameter of a model. But number of weights, they are called parameters of the model. Right? So there should be a difference. We should know the difference between hyperparameters of a model and parameters of a model. Hyperparameters mean decision. If you have a decision tree, we'll talk about this. The height of a tree. If you have a linear regression, the number of coefficients. This is a hyperparameter. But the coefficients, they are parameters. Okay, let's talk about, again, very quickly, what do you mean by algorithm versus model? Right? So in linear regression, for example, we produce a model. There's a vector of values of the coefficients of the model. For example, in decision tree algorithm, we produce a model comprised of a tree of if-then statement with specific values, right? So we form a tree in decision tree algorithm. So that tree is a model. Similarly, in neural network, we use back propagation and gradient descent to and forth to produce a model that is comprised of trained weights. And those weights define your neural network, your model. This is what we talked about. So we talked about this last time. So we also talked about supervised learning, a very quick overview. In supervised learning, we receive a set of inputs along with corresponding correct outputs to train a model. Right? So we have our data, and data is labeled. I will define formally in a while what do you mean by a label, what do you mean by features. Right? But we talked about this supervised learning in the last lecture. An example of supervised learning we categorize into two classes: regression, classification. If we have a problem in which we want to carry out quantitative prediction on a continuous scale, the problem is referred to as regression. Right? Examples could be prediction of age of a person from his or her photo, right? Or it could be, say, we want to predict a price of a 10 Marla 5-bedroom house in 30 years time. Right? So what could be exchange rate after 1 week? Or it could be efficacy of Pfizer COVID vaccine. Or it could be prediction of average temperature rainfall during monsoon. Or it could be cumulative score in machine learning course. Right? What do you expect? Probability of decrease in the electricity prices in Pakistan. Right? Nonetheless, you can predict it, right? Number of steps you take per day, right? Say after in a week time. So what do all these problems have in common? The predicted value is quantitative. That is on a continuous scale, right? So we have continuous outputs. So we summarize regression that predicting continuous outputs is called regression. So regression is nothing new. It has been, people in statistics had been using regression for decades, even I think for centuries. Right? But we will give we will review a machine learning perspective to regression. Right? Effectively, we will be using the same concept which has been used in statistics. So I assume you're now clear what do we mean by regression. Right? So in supervised learning, what do you mean by regression? That's on a continuous scale. Yeah, you can take a small step, and you can take half a step right, and you still take back. Yeah, I would call it it's a continuous thing. So in classification, the difference from regression is given a data sample, predict its class. The difference between regression in classification is now the value we want to predict has discrete values, right? For example, prediction of gender of a person using his or her photo or handwriting style, or spam filtering. This is now enabled in every mailbox, right? So you get an email, and the spam filters determine whether this email is a spam or it's not a spam, based on the content of the email, right? Or object or face detection in a photo, or will back on campus on February or not. Yeah, right? Yes or no. So temperature, rainfall, normal or abnormal during monsoon, the next year probably. or letter grade in ML course. If you talk about cumulative score in ML course, that is regression. If you want to predict letter grade in ML course, it's classification. Hang on. Decrease expected in electricity prices in Pakistan next year. Yes or no? Or whether you will take 10,000 steps taken today or not, right? So given some values from sensors of your phone, or say your weight, the calories you burn, somehow you can use that data, and you want to predict whether you have taken 10,000 steps or less than 10,000 steps. So what you want to predict is yes or no, binary. Right? So what do all these problems have in common? So the output is what you want to predict is discrete, or it is categorical. Right? If we have only two choices, yes or no, we call it binary classification. Right? So gender of a person, it's a binary classification. Spam filtering, it's a binary classification. If you have multi classes, for example, letter grade in machine learning course, that is multi-class classification. We have multiple classes. Or we can summarize that predicting a categorical output is called classification. Any questions? Okay. Okay, let's move forward. We talk about the nomenclature which we'll be using in machine learning, or just for supervised learning. Right. So we'll be setting up a supervised learning problem. Right? The nomenclature we use, the terms we use in in supervised learning. Okay. In these regression classification problems, what do we have? We have inputs that are referred to as features. We have outputs, which we refer to as label. We will have training data, which is in fact input-output pair, and for which the output is known, and this training data is used for training a model by machine learning algorithm. We also use the term a loss, an objective, or a cost function. So this loss function, अभी हम इसको formally define करेंगे mathematically. So what do you mean a loss function? Right? A loss function determines the performance of your trained model. And finally, the test data, input output for which the output is known and is used for the evaluation of performance of the trained model. So we will not use test data for training of the model or during learning. So let's look at one example. Okay, we have this example in which we have interest rate, we have unemployment rate, and we have stock index price. And using interest rate and unemployment rate, we want to predict the stock index price. So the value we want to predict is stock index price given interest rate or unemployment rate. Is this regression or classification?
Regression.
It is regression. Great. What are features here? Input to a model is, okay, what do you want to predict? Stock index price given interest rate and unemployment rate. So inputs are interest rate and unemployment rate. Yes. So we can say these are our inputs. So what is the label? Output, right? Stock index price. And for these three instances, can you see my screen? Hang on. I think now you can see my screen. Now, cursor. Yeah. For these three instances, we do not know the output. Say for these three instances, we want to predict the stock index price given interest rate, unemployment rate. But for all other inputs, we know the output. So we can use all the other data for training. So all of these input output pairs would form a training data, right? So this blue is input, this brownish yellow is your output labels, and this is when you combine these two, concatenate these two, what you get as our training data. Any questions? Okay, so this is
Sir,
just,
I have a question.
yeah, sure.
Why are you calling all of that training data? Shouldn't we split some of them into training and testing?
We will split it very shortly in just half an hour. Yes, you're right.
Oh,
All of this is not, this all is a training data, but we won't use all of this for training. This is in fact our data for which the label is known, for which the output is known, right? We call it training data, but we won't use all of the data for training. We will split it, and we'll get to the reason why do we split. Okay, I hope I have answered the question.
yes, sir, you have. Thank you.
Thank you, Maria. So let's mathematically formulate these input, label, and training data. So I will again stick to the same example, and we formulate. We assume that we have D columns, so features of the input. So in this example, we have D is equal to 2, right? So for each sampling point, or for each data point, we have 2 inputs, we have 1 output, right? So D, number of columns, number of features, number of inputs. So D here, in this example, the D is 2, right? But in general, D can be, it could be 10,000, or it could be in tens. So we will be using this Xi to refer to the features of the ith sample, right? So Xi, what is the size of Xi? Number of features, right? Xi1, Xi2, Xi3, Xid. So Xi1 is the first feature of the ith input. Hang on. The first feature of the ith data point. This is right. If yi, so we use yi to denote the label that is associated with the input xi. And we formulate, we concatenate these two, and we form a vector by concatenating input with the label. And so we have these input output pairs. So how many inputs do we have? We use small n to denote the number of data points we have in the training data. In this example, n is 21. Okay, I summarize. We use x subscript I. I represents ith data point. So x, we use x to denote input, y to denote output. Subscript is used to denote data point. What is the size of x? The number of features. Right? Here I have taken y as a scalar, but y can be vector as well. Right? So we can have a vector. We can predict vectors, right? But we will see this as we progress in the course. Any questions? Okay.
So
Mhm.
y label y component is the output of our system.
Yes, y is the label. We're using y to denote the label. That is, yi is the label associated with xi input.
So each input has 2 features, like in this case.
In this case, yes, xi belongs to xi is two-dimensional, and y is a scalar.
Okay, so with two-dimensional input xi, we get a scalar quantity y.
Yes, so we want to learn a model. We want to learn a function that maps these two values to this one single value. Right?
So thank you.
Yeah. So your model would have two inputs and one output. Okay. So using this adopted notation, we can define what we call training data. We can concatenate these two input-output pair, and we stack all these data points together. And what we get is this set, which we call training data. So this set would be is a subset of this space, which is x superscript d times y. Right? Let me define what we mean by xd and y. Right? So xd is the d-dimensional feature space, and y is the label space. In the previous example, so what was, we had x2, and in fact x2 is, in this example, x2 is r2, right? Because interest rate can be a real number and unemployment rate can be a real number. So in this example, the input space is r2 and output space is also a real number. It's also real. Right? So in regression, the output space or the label space is always a set of real numbers because we are predicting on a continuous scale. Whereas in classification, we can have y could be 0, 1, or you can call it -1, 1, or you can call it 1, 2, you can call it a, b, binary classification, right? So cardinality of y, right? The size of y indicates the number of classes you have, right? So if you have binary classification, the cardinality of y is 2. If you have a multi-class classification, for say you have an m-class classification, your label space would have m classes. So I have indicated as 1, 2 to m. These are just labels, right? It could be so a, b, c, d, and on going on, right? Or it could be some categorical variable as well, right? But this is the idea is the cardinality of the label space in classification determines the number of classes. Okay, let's review these concepts with the aid of examples.
So may I ask a question?
Sure, yeah, please.
So just for clarity, is the cardinality of the label space limited to 1 in the regression case?
No, infinite, isn't it?
Okay. Right, sir.
Well, we have a continuous scale. Yeah. If we take this example and we have a data of 200 patients, right? And say we have a model H, which we want to learn. So we have input as age of the patient, cholesterol levels, glucose levels, BMI, height, heart rate, calories intake, number of steps taken, right? And say you want to predict the saturation level at some point in time. So what is D here? So you recall, what does D represent? Number of features. So we have 1, 2, 3, 4, 5, 6, 7, 8. So D is 8. Agree? And what is N here? Number of data points. So we have 200. And what's the label? What's the label space? Set of real numbers. In fact, it is a subset of R, right? because oxygen saturation is usually made in percentage. You only get from 0 to 100. It's a subset of real numbers. So to be mathematically, to be very precise, label space in regression is a subset of real numbers.
Sir, I have a question.
Sure.
Sir, shouldn't the dimension be 1 in regression of the output?
No, the output itself is a scalar. Yes,
Acha.
output itself is a scalar. Yes, yes, but it belongs to a set of real numbers.
Okay.
And it can take any value in R. Okay, move towards next example. Say you have a very well-known, very popular MNIST data, right, in which we have handwritten digits. In this data, we have 60,000 samples for training data and 10,000 samples for testing data. And each data point is a 28 by 28 pixel image. What is D here? Yeah, 28 cross to 784. Right. So if this is a grayscale image, right? So each data point, each feature would represent, right, a number between 0 and 255, right? The intensity of it. If this is an RGB image, what is D then? 28 by 28 times 3. So the feature space would be very large. Agree? Yeah. So N here is 60,000, and we want to predict, say, given this handwritten digit, we want to find the correct label. I hope this is clear now. This is a multi-class classification problem, and we have 10 classes. Right?
How did you get the last?
Pardon?
28 into 3. How did you get the 28 into 28 into 3, please?
Because each pixel would have 3 values: R, G, B. If I think I can write on this one. Hang on. Yeah, it could be. So each pixel is RGB. So how many pixels do we have? We have 784 pixels. Right. So each pixel is a 3-dimensional itself, has 3 components. So therefore, in total, we have 28, 28, 28 times 28 times 3 features. Clear हो गया आपको नहीं हुआ ये? ठीक है हमसा. Okay, so these were 2 examples just to illustrate how do we formulate the training data, and how do we characterize the dimensions of the data. Right. So given the training data, let's talk about how do we learn from the training data. Right? Let's talk about learning. Okay. So if we recall a problem in hand, so what we have is, we have our training data and we want to develop a model that can predict the label for the input that is known, that is not part of the training data, or that for which the label is unknown. Right? That is our problem, right? And the underlying assumption is the data points X, I, Y, I, so they are drawn from some unknown distribution, which we denote by P. So the distribution is unknown. If the distribution is known, we can determine y given x. The overall idea is in fact that we use training data to estimate this distribution. So in the previous example, label was stock price index that we wish to estimate using what was the two variables, interest rate and unemployment rate, right? The training data is drawn from some distribution. If you get the data only from the US market and you train the model and you try to learn, say, what was the output variable? Stock price index for Pakistan, that model won't work because you're getting the training data from some population, from some distribution that is not capturing the overall variations, overall dynamics, overall relationship between input and output, right? So for this problem in hand, our goal is to learn the machine. We call it model, we call it function, or in some textbooks, it is referred to as hypothesis. So we want to learn this hypothesis such that if you get a new pair from the distribution P, we can use this H to obtain, this H should give us Y that is associated with the X. And we should obtain this Y with high probability, or this model, this hypothesis, this function, this machine should be approximating Y in some optimal sense. We will describe shortly what do we mean by optimal sense. But this function H, this model H, what is H? H is referred to as hypothesis that is capable to map X to Y. Agree? Any questions? So what we want is, we want to find H that is capable to map any X from this distribution, and that gives you Y that is associated with that X. Any questions? Okay. Before we can find a function H, we must specify what type of function it is. What type of function we are looking. So H can be, there can be tons of choices of H. So H can be a linear model, it can be a neural network, it can be a decision tree, and so on and so forth, right? So we call the set of all possible functions H can take as hypothesis class. Okay? So I'm defining a new term here, hypothesis class. So hypothesis class is a set of all possible functions, all possible choices of H. Right? So hypothesis class के अंदर it would be a big set that contains all the models, and we call that set as hypothesis class. Any questions? Okay, let's talk about hypothesis class. Let's denote it. So we denote the hypothesis class by this math call H, calligraphic H. And for a given problem, we wish to select hypothesis from this hypothesis class. And the question is how? So we define hypothesis class H for a given learning problem, right? And with experience, for a given learning problem, we will learn and or I'm seeking it that what are the possible candidates that can populate, that can form hypothesis class H. So once we have hypothesis class H, right? Again, H is a big set, right? That can has multiple functions, multiple models, multiple machines. And we want to evaluate the performance of each candidate function in hypothesis class. And we pick the best one. We need to answer, what do we mean by the best one? How can we find the best function? For this, we need some way, we need to define some metric to evaluate what it means for one function to be best than the other function. Agree? This is where the loss function comes in. So a loss function evaluates hypothesis on our training data. Okay, how do we evaluate the performance? We define a loss function to quantify the accuracy of the prediction. So as the name suggests, the loss function quantifies the accuracy of prediction. The higher the loss for a given H, the worse the candidate is, right? A loss of 0 means we have the exact model which we are looking for. It is common practice to normalize the loss by the number of data points we have in training data, so that what we get is our loss would be a measure of error or loss per data point. If you don't normalize by the number of data points, if you have a large data set, you will get a large value of the loss function. Right? So when we compute loss function, when we define loss function, in the definition of loss function, we always divide by the number of data points. Okay, so we usually use capital this calligraphic L to denote the loss function, right? So a loss function computes the power of H to predict Y given input X. Okay, let's talk about the 0-1 loss function. So we define.
Sir, I had a question.
Yes, yes.
सर मैंने पूछा था वो जो शुरू में जब आपने हमें टेबल दिखाया था जिसके अंदर हमारी एक ट्रायल डेटा थे, एक तो हमारी ट्रेनिंग होता है और फिर हमारा एक टेस्टिंग होता है। तो टेस्टिंग वाले के लिए आउटपुट के आगे वो क्वेश्चन मार्क्स लगे हुए थे। तो इज इट कि हमने जो टेस्टिंग है उसका हमारे पास प्री डिटर्मिन्ड आउटपुट ऑलरेडी होती है और फिर हम उसे सिस्टम में डाल के देखते हैं कि आउटपुट सही है या नहीं, या फिर उसकी आउटपुट प्रेजेंट ही नहीं होती?
Very good question, Fatma. So that was not testing data. So that was a data for which the label is not known. For testing data, we will know the label. We should know the label. Otherwise, we cannot test, we cannot evaluate the performance of our model.
और उसी से फिर हमारा लॉस फंक्शन डिटरमिन होता है कि हम हमारी जो पहले जो हमारी मॉडल से वैल्यूज आ रही होती हैं फिर हम उन्हें कंपेयर करते हैं और जो पहले से आउटपुट वैल्यूज होती हैं उनसे।
बिल्कुल ठीक है, बिल्कुल ठीक है. We will formally define loss in part, right? Using we will split. Hamza, yes.
Sir, sorry for cutting in, but testing data and training data are the same things, right? In this context.
Yeah. The training data is defined as input-output pairs for which you know the output corresponding to input, right? So we have association. We know for a given input, we know the output. So we split this data into two parts, right? And we'll talk about splitting now. Yes, if input for a given input, the output is known, that data point can be part of training data, or that data point can be part of testing data. But for both training and testing, output is known, label is known. Okay, any questions? Okay, let's define loss function. We begin with the defining a very basic definition of the loss function, or very simple loss function, which we call 0-1 loss function. So let me mathematically define it, and then we will talk about this. Right. For a given age, so I define the loss function. Subscript 0-1 indicates it's a 0-1 loss function. It is computing loss for a given age. So the argument is h. H is a model, right? It's a machine, right? It's an argument of the function. And you should be comfortable with this notation. Right? Is equal to, why do we have 1 over n? Normalizing. We're normalizing with the number of data points we have in the training data, right? And what we have after the summation, this is called Kronecker delta, or if you're studying signal scores, if you have read signal scores, it's a simple discrete impulse function. So it's a discrete impulse, right? Which is mathematically defined as if the subscript of this delta is 0, it takes the value 1. Otherwise, it takes the value 0. Right? So if you stick to this definition, if you follow this definition of delta, what is loss quantifying? So what do we have in the subscript of delta? H of xi. What is h of xi? The output.
The output of the hypothesis.
Excellent. The output given xi. Bilkul. Or what is yi? And the actual output associated with xi, the true label, right? That means the difference between these two is a subscript of delta. If this difference is not 0, right? What did you get?
Zero.
You get 0, right? Otherwise, you get 1. So what about loss function? If there's too much mismatch, what's going to happen? The subscript won't be. Hang on, I think there is some issue with here. It shouldn't be defined like this. It should be, let me define other way around. So this delta is all right. Just give me a second. This delta hxy minus yi. Hang on. I should be defining probably or minus this. So if there is a mismatch, and then this should be 0, and the loss should be contributing, right? I think this is right now. Yeah, my apologies. Yeah. So if there's a mismatch, then the delta would be 0, and it should be, hang on. Yes, the loss will be closer to 1. If too much mismatch, it will be closer to 1. If h of xi is not matching with any of yi, then the loss would be 100%, exactly 1, right? Because all of this would be 0. Right? So what's the interpretation of this loss function? Yeah. So first of all, we note that there's a normalization in the number of samples, right? And this loss function simply counts the number of mistakes made by hypothesis function on D. So we usually, this 0, 1 loss function is not used very frequently. The reason is this is not differentiable, and this is also discontinuous. And therefore we do not use this 0, 1 loss function very frequently to quantify the loss. In some applications, in classification, at times we use this 0, 1 loss function, and we will use, and there you can better understand that why do we need the 0, 1 loss function and what are the implications. But the primary reason is this is a non-differentiable, this is discontinuous as well. Okay.
So I have a question.
Mm-hmm.
Sir, in the previous slide,
Mm-hmm.
sir, are we dividing by n because we want to take the average of the loss of every example?
We want to define loss per data point.
Okay.
Say, for example, if you have a data set of 100 points, right?
Hmm.
The maximum value of loss would be 100. Maximum possible value would be 100, right? If a data point, say, has 1000 data points, then if you don't normalize by 1 over n, the maximum value of loss can be 1000.
बिल्कुल ठीक है.
1 over n, this is normalizing. And so this brings the loss between 0 and 1.
0 and 1. ठीक है.
ठीक है समान. हारिस.
सर मैंने ये पूछना है कि इसमें the error will be either 0% or 100%. There's no in between.
No,
Right.
they can be in between.
For a single data point, for a single row in the data set.
For a single, yes, it can be a 1 or 0.
Okay.
That's why we've been saying that the interpretation of 0, 1 loss function is it's simply counting the number of mistakes made by hypothesis function on D. If hypothesis function can predict y exactly, we say the error is 0. Otherwise, the error is 1. That's why we call it 0, 1 loss function. ठीक है जी? Okay, great. I hope no one has raised hand. Yeah. Let's also define one more loss function, which is the squared loss function. As the name suggests, is also called mean square error, mean square error, MSE or mean square error. Okay. Before I define it mathematically, you can just think about this. As the name suggests, it's mean squared error. Right? You take a difference is error, you square it, and you take a mean, right? And that's what it is. Right? So this term inside the brackets is called the difference between the error and the difference between predicted value and the true value. You square it, you square the error, and you sum and divide by 1 over n. This is taking a mean, right? Mean square error, or MSE. Right? What's the interpretation of MSE? So, okay, the loss is always non-negative, but the loss grows quadratically with the absolute error amount in each sample. So due to this property, the significance of this property, that no predictions to be really far off, or the penalty would be so large for a far off value such that different hypothesis function is likely better suited. अगर किसी एक डेटा पॉइंट के ऊपर वैल्यू एरर बहुत ज्यादा है, the squared operation would boost it, right? Would amplify it, due to which the value of loss would be higher. And there's a flip side of it. If the error is say 0.01 and you take a square of that, that would make it 0.0001. अगर एरर बहुत छोटा है तो उसको डिमिनिश भी कर देगा the squaring operation. But the error is large, that can amplify the error. But usually due to the later property, we use squared loss function very frequently. Something very closely related to squared loss function is the root mean squared error. Right? So as the name suggests, that is simply square root of the mean square error. You square, so root mean squared error. You square, you take a mean, you take a root. Okay, let's also define one more loss function, absolute loss function. And again, the name suggests it's just the mean of absolute value. Absolute values of the error. So the interpretation is that loss grows linearly with the absolute of the error in each prediction, right? So in mean square error, अगर loss ज़्यादा है किसी एक data point के ऊपर, तो squaring operation boosts it. But in the absolute loss function, the loss grows linearly with the absolute of the error in each prediction. And we use this absolute loss function for noisy data or in regression. Finally, I note that all of these losses are defined, so all of these are non-negative. Okay, so we have defined loss function. हम चले कहाँ से थे? हमारा ऑब्जेक्टिव क्या है? हमारा ऑब्जेक्टिव ये है कि our goal is to learn the machine age such that we can age to obtain the predicted value of y in some optimal sense. Right? So we have different candidates in the hypothesis class. Right? And for each candidate, we want to evaluate the performance using training data and choose the candidate which is the best one. And now we have a measure to quantify or to evaluate or to determine the best one, right? And that's the loss function. So using all of this formulation, I'm going to define the problem mathematically, the learning problem. Okay, the learning problem we have is we wish to select H from the hypothesis class such that H star is minimum, that minimizes loss function over the hypothesis class, right? You should not be afraid of this notation. Let me make it very clear to you. So,
Sir, a question, sir.
Mustan sir, yes. जी क्वेश्चन बेटा पूछें मुस्तान सर।
जी सर, में क्वेश्चन था कि जो हमारी हाइपोथेसिस का सेट है उसमें तो जैसे आपने कहा कि न्यूरल नेटवर्क्स हैं, डिसीजन ट्रीज हैं, मतलब कि ये वाले जो हाइपोथेसिस क्लास है ये तो हमारी प्रॉब्लम टू प्रॉब्लम वेरी करेगा ना?
एग्जैक्टली
ठीक है,
एग्जैक्टली
तो मकसद है कि हम पूरी जो हाइपोथेसिस का सेट है उसके ऊपर हम अपना जो डाटा है उसको क्यों उसके ऊपर ट्रेन करेंगे, मगर ये कुछ कंफ्यूजन इसमें हो रही थी।
We don't know which one would work best.
अच्छा,
हमें तो नहीं पता,
सेम।
right? This is, but with experience, we will learn that for this nature of problem, I have these bunch of possible options for hypothesis class. Right? But this is
बिल्कुल ठीक है।
generalization. Right? So we have a large set with hypothesis class, and we want to scan over hypothesis class, and we want to minimize loss function by scanning over hypothesis class.
Sir, I've got a question as well.
पूछे बेटा।
सर, जो सारे लॉस फंक्शंस आपने डिफाइन किए हैं उसमें आप कंपैरिजन कर रहे हैं yi से, राइट? तो this assumes that we know the exact mapping between xi and yi. So this means that the loss function can only be evaluated using the test set.
No. So here, no, the learning is on the training data. So you evaluate the loss function. We will evaluate the loss function on the testing data. Yes, you're right. अभी हम इसको split करते हैं तो वो हम इसको भी. So what I've written here is a very very generalized thing. अभी हम इसको specialize करते हैं by splitting training into multiple parts. ठीक है मोहसिन?
सर एक और चीज, जब हम हर हाइपोथेसिस को जो हाइपोथेसिस क्लास में उसे उसका लॉस फंक्शन फाइंड करते हैं, फिर उसमें सब मिनिमम फाइंड करते हैं, बट व्हाट इफ लाइक मल्टीपल लॉस फंक्शंस में से जैसे एक नॉर्मली को ज्यादा पीनलाइज करता है जो क्वाड्रेटिक के लीनियर इतना नहीं करता, सो ये हो सकता है कि मल्टीपल डिफरेंट लॉस फंक्शंस के लिए हमारी डिफरेंट हाइपोथेसिस बेस्ट आ रही हूँ, फिर हम उस केस में क्या करेंगे?
Exactly. So it all depends what was your objective. So it's a very very good question, right? When we say we minimize loss function, what I've defined here is that means now I have selected my criterion. Now I know that I will be using this metric or this loss function to select my candidate. Obviously, if you change the metric, if you change the loss function, there would be another candidate. There's a possibility that, in fact, there is a possibility, or there must be a possibility that another candidate minimizes the loss function for a different, minimizes different loss function. So it all depends that whether you want to minimize 0-1 loss function. So 0-1 loss function is very very harsh, right? That what you want exactly equal prediction. So you're not making any room, 0 or 1, right? Or whether you want to minimize mean square error, you want to minimize mean absolute error, right? So I have talked about interpretation of these errors, right? So what is mean absolute error? That grows linearly with every erroring every data point. This indicates that, okay, what's the interpretation? Interpretation is you expect the error would be, total error would be uniformly distributed, or on average, it will be uniformly distributed across each data point. But if you talk about mean square error, then there's a possibility that would be penalizing the large values of the error. The square error person would boost them. Coming back to your question, the answer is you can change your metric. You will have a different minimization problem, and you can have a different candidate from the hypothesis class. It all depends what do you want to minimize. That's why I've defined loss functions earlier, and here this L can be anything here. There is an area of machine learning. In fact, lots of people in machine learning, and they focus on the question, how to do this minimization efficiently. They devise algorithms. How do they carry out this minimization? How do you read this? You should be very comfortable with this. This is nothing but just a formulation of an optimization problem. Right? So what is the problem here? You want to minimize the loss function. The value of the loss function depends on h, and you have different candidates in the hypothesis class. You scan over hypothesis class, you pick h for which L of h is minimized, and you call that h star, right?
सर एक क्वेश्चन था सर सर जिस तरह हमारे पास जो एच है उसमें भी मल्टीपल कैंडिडेट्स हैं, इस तरह जो हमारे पास जो लॉस है उसमें भी मल्टीपल कैंडिडेट्स हैं, तो फिर तो हम इस तरह नहीं करेंगे कि मिनिमाइज करें हर एच को हर लॉस के अगेंस्ट, और उन सब में से हम देखें कि जो मिनिमम हमारा ऑब्जेक्टिव है वो किस लॉस एंड किस हाइपोथेसिस क्लास ने अचीव किया है.
Mustan sir, it depends on the nature of problem. For example, in some problems, you want to minimize mean absolute error. In some problems, you want to minimize mean square error, right? A very classical example would be what we call one norm minimization versus two norm minimization. So in two norm minimization, we are minimizing a square, and in one norm minimization, we're minimizing the mean absolute error. It depends on the application. It depends on the nature of the problem. It depends on what you desire. Because one h, there's a possibility that for one loss function, you get a different h, and for another loss function, you get a different h. Okay, अभी हम इसको सेटअप कर रहे हैं. हम इसको भी जब टेक अ स्टेप फॉरवर्ड, हम इसको मैथमेटिकली सबको फॉर्मुलेट करेंगे, फिर चीज़ें और क्लियर हो जाएंगी आपको इंशाल्लाह. ठीक है जी. Okay, we just recall the data points we have. So they are drawn from some unknown distribution. There is a possibility that we find a function h after solving this optimization problem, and that candidate function, that machine, is giving us low loss on our data. But how can we ensure that this hypothesis H will also give low loss on the input that's not in D? Right? If you use all the data points you have for learning, so what do you have? You have data points that are drawn from some unknown distribution. You don't know the distribution. There is a possibility that your data points are only capturing some of the parameters of distribution, or they are not a true representation of the distribution. And this would happen when the data is not capturing the data you have is not capturing the variations in the distribution. So you solve optimization problem, you get H, but that H is giving you loss, that H is giving you low loss on D. And if you take any other, but what do we do? हम चाहते ये हैं, what do we want is that we want to ensure that hypothesis H will give low loss on the input that is not in D. That's the whole idea. Agree? To illustrate this, I'm going to consider a model that is trained on every input in D that is giving zero loss. Let me explain this. So say you have this candidate H. How do you interpret this? So this H is giving, this H takes X and returns you y, the output. Takes input, returns output. And for any input x, it returns you yi if that x exists in data point. अगर वो डेटा पॉइंट में हिस्सा है, आपके ट्रेनिंग डेटा का हिस्सा है, तो आपको वो y रिटर्न कर देगा. अदरवाइज कहेगा आई डोंट नो अबाउट दिस x. That means के हम इसे we call it memorizer, right? So it is not capable to give you output y for any x that is not part of D. Even there's a possibility that there exists xi in D which is very close to this x, but your memorizer would say, I don't know about this x. This is not known to me. Right? What is the consequence of this? This model would only work on the data points. In fact, there's no need to learn.
कोई भी unknown data जो होगा उसके लिए work नहीं करेगा.
Exactly. You won't get anything. In fact, for this memorizer, we don't need to learn. You already know the y for any x. You just need a lookup table, right? For x, if x is in the lookup table, you pick up y and you return it. If x is not part of lookup table, you return 0. So that's the whole learning, right? The interpretation of this is, so you get 0% loss error on the training data. Is it right? Oh. Do you think this is right? Yes. We get 0% loss error on the training data because model is fed to every data point in D. But if you give any unknown input, obviously you get error. You will definitely get error. So your model is 100% fit on the training data, on the data you have, but your model is not capable at all to predict output for any unknown input. So this is overfitting. This is the first glimpse of overfitting. So your model is fit, your model is trained, your model is tied to every data point you have, but the model is not capable at all to predict for any unknown data point. Right? So आपने model को बहुत complex कर दिया है. For example, if you have 6,000 data points, right? That means your model would have 60,000 parameters. Every input is a parameter. For every input, you need an output. Right? You need to store all the data in the form of lookup table. You get an x, you pick scan x, this column, and you pick y, and you return it. Agree? Okay. So we revisit the question we have.
Kindly दोबारा बता दें.
Right. Okay. For example, we talk about the relationship between, say, body mass index. Okay, maybe we talk about, we take a regression problem, right? So we want to predict temperature at any point in time, right? At some place. So given some other parameters, right? If those first you have training data, in training data you have parameters, and you have the corresponding temperature, right? You have training data, you have the corresponding temperature. So you have 60,000 values of these parameters, and you have 60,000 labels. If you get a different parameter here, ideally or intelligently, you should be looking कि जो ये वाले पैरामीटर हैं इस सेट में किसके करीब हैं. That would be the very intuitive, a very simplistic approach. And you would say okay, these parameters are nearest to this data point, so I can say this would be corresponding to this closest feature vector. You pick the output and you say for this unknown is not here. For this unknown, because this unknown is closest to this data point, so this y is your desired, you expect it. This y is your prediction. But what this memorizer is doing, if this memorizer is not able to find the data point in this column, it returns 0. Right? So it's not doing any intelligence, it's not doing any learning. Right? So मॉडल किस तरह का है हमारा? मॉडल मेमोराइजर है, वो इन हर डेटा पॉइंट के ऊपर फिट हुआ है. अगर आप जिस डेटा पॉइंट के ऊपर ट्रेन हुआ है, अगर आप वही डेटा पॉइंट दे देंगे तो वो आउटपुट दे देगा. If you give some other data point as an input, you will get 0 output. So हम कहते हैं इसको we call it कि मॉडल बिल्कुल ओवरफिट हुआ है ट्रेनिंग डेटा के ऊपर. ठीक है जी?
जी सर.
Okay, we revisit our question. How can we ensure that hypothesis will give low loss on the input, not in D? So this was a question we had. So our objective is we want to find H that minimizes loss function. What we have is training data. But we also want to ensure that H will give low loss on the input which is not in D. And the answer to this question is train test split. So what is train test split? So now we're generalizing, right? So we split data into, hang on, let me skip this slide here. So to resolve this overfitting issue, we split data into train and test subsets. So we have our training data, it's going to be D ka tha. We split this data into 2 parts. So one part is called a test part or test data, and the other one is the training data. There are different techniques to split. You can use 70-30 splitting in terms of percentages, or you can carry out 80-20 or 90-10. So there's no clear rule of splitting. You can use any other methods, but these are the conventions used in machine learning. You can carry out 70-30 splitting, 80-20 or 90-10.
सर जब हम डेटा पॉइंट्स लेते हैं उसके अंदर डू वी अज्यूम कि इसके अंदर डेटा पॉइंट्स रिपीटेड नहीं है, लाइक ये सारे यूनिक है, कंसीडरिंग अगर रिपीटेड हो तो उससे बायस नहीं आ जाएगा इन आवर फंक्शन?
बिल्कुल बात करते हैं उसकी.
ठीक है.
How to carry out the splitting? Right. Split should be capturing the variation in the distribution. So the commonly used methods are you carry out, if you have a data that is in the form of time series, right? So you carry out splitting against time, right? Say you have seasonal variations for say 2 years. You keep 1 year and 9 months for training and the next 3 months for testing. That's how you carry out split. For time series, and the usual method is splitting versus time. Splitting with respect to time. And the reason is when you have a time series always has memory, right? That is something varying with time. The output at time instant t would have some relationship what's going on in the previous time instances. And therefore, we carry out splitting with respect to time. If you have a data that is not does not have temporal variations, the splitting is carried out randomly, and usually what we call IID, identical independent distribution, to carry out splitting. So you uniform, you pick, if you want to carry out 70-30, you uniformly distribute, uniformly pick 70% and randomly pick, uniformly and randomly pick 30%. Right? And yes, we need to take care that the data point in the testing, in the test data, should not be part of the data set in the training data. So this is usually carried out by removing the instances in the data point in the data set which are same. Right. Okay. Once we have the splitting, we use the test data set only for modeler training. Right? But what's going to happen if we only use training data for training and testing data for evaluation of the model? That means during learning, we cannot evaluate the performance of our model. We cannot quantify the loss function on the unseen data. There's a possibility, when you're carrying out training, the model is again overfitting to training data. When you test on testing data, you get a large error. Right? This is very similar to what we had earlier in the memorizer case. You have our training data, the memorizer is trained on training data, but the model is not trained on testing data. So on test data, you will get a very, very large error. To incorporate this splitting during the learning, we again split this training data into two parts. So we call one part as validation, and the other part is called training data. So during learning, we train on this blue data and we evaluate performance on validation data. Right? If you're not getting the desired accuracy or the desired loss on validation data, you change the model, you change the hypothesis. So this method is usually called n-fold cross-validation. Right? Here I have illustrated 5-fold cross-validation. So we divided data into 5 portions. You take 4 portions for training and 1 for evaluation. So again, 4 for training, 1 for evaluation. This is 5-fold cross-validation. Okay. So this validation data is used to check whether the hypothesis which you obtain using training data does not suffer from the overfitting issue. Right? If there's no validation data, you cannot avoid overfitting. Right? You need this validation data to avoid overfitting. Right? Any questions? For C, and do we change the hypothesis or split the data differently? You do the both things. Yep. You keep on splitting. You keep on splitting the data differently, and you also, if after multiple splitting you're not getting the desired loss, you change the hypothesis.
सर क्वेश्चन था अभी आपने कमेंट किया कि अगर वैलिडेशन स्प्लिट अगर हम नहीं करते तो ओवरफिटिंग जो है वो आ जाएगी, तो हमने ओवरऑल जो डाटा था उसे ट्रेन टेस्ट में जो है वो ऑलरेडी स्प्लिट किया है। फॉर एग्जांपल हम 60-40 में हम स्प्लिट कर लेते हैं, तो अभी भी हमारे पास जो है ओवरफिटिंग जो है वो अकर कर सकती है अगर हम वैलिडेशन में स्प्लिट नहीं करते ट्रेनिंग डाटा को।
टेस्टिंग डेटा इज यूज्ड फॉर evaluation of the performance evaluation of your model once it is trained. Okay, okay, what's going to happen? You keep on increasing training data, right? The error would keep on converging. Error on training data, right? देखिए वो ट्रेन जो हो रहा है वो तो ट्रेनिंग डेटा पे हो रहा है. The model has not seen testing data. Once the model is trained on a training data, it is already overfitting. वो ट्रेनिंग डेटा को वो ओवरफिट हो गया हुआ है, राइट? हम टेस्ट डेटा को सिर्फ उसको उसकी परफॉर्मेंस को एवेलुएट करने के लिए करेंगे, यूज करेंगे.
तो जब हम लॉस मिनिमाइज करेंगे वो असल में फिर हम वैलिडेशन का लॉस जो है वो मिनिमाइज कर रहे होंगे.
एग्जैक्टली अभी हम उसको मैथमेटिकली फॉर्मुलेट करते हैं. एग्जैक्टली, यू आर एब्सोल्युटली राइट. ठीक है जी.
Sid,
Mm-hmm.
has the model seen the validation data?
During training, yes. You train on the training data and you validate on the validation data.
So validation, you first train the model on the training data and then you take part of that training data and then check for overfitting.
No. आपने जो लॉस फंक्शन एवेलुएट किया, आपने ट्रेन किया ट्रेनिंग डेटा को यूज करते हुए, और जिसको मिनिमाइज कर रहे हैं, that loss function is evaluated on the validation data. So the overall idea is you want to check whether your hypothesis does not suffer from overfitting.
Okay, so first we train it and then we so the validation data, then the machine has seen the validation data before, right?
Yeah, so you compute the loss using validation data, and if the loss is, say, very large, we do the revision, right? So क्या करते हैं, you will carry out different splitting, right? आपने ट्रेन किया 4 पोर्शंस के ऊपर और आपने वैलिडेशन के ऊपर लॉस को एवेलुएट किया, right? You're not getting a desired loss, right? That means आपका डेटा था. So again, during training, the model has not seen this validation.
Okay.
It's called training with cross validation. आपने इस पे ट्रेन किया, इस पे लॉस एवेलुएट किया. अगर लॉस डिजायर्ड नहीं है तो you will carry out different splitting of this training data.
Okay. All right, sir. Got it.
For example, in this is 5-fold cross validation, right? So you train on this blue part, you evaluate loss on the validation, and you keep on doing for these 5 cases, right? You pick the model, you pick your hypothesis for which the loss on validation data is minimized. ठीक है? Okay. अगर हम सारे को जनरलाइज करें, एंड प्रीवियसली हमने कहा कि we split into training and test data, so but we also split into validation data as well. So we divide our D into 3 parts: training data, validation data, and test data. And once we have these 3 data sets, we choose H from the hypothesis space using training data along with validation data, but finally we evaluate H on the testing data. So this is the overall generalization of train, test, and split. Train.
Sir, can you go back to the previous slide, please? सर इसके अंदर पहले एक दफा हम टेस्ट और ट्रेन में स्प्लिट कर लें, उसके बाद जब हमने वैलिडेशन के लिए की है तो जो हमारी ट्रेन डेटा उसको हमने बेसिकली अगर 5 फोल्ड वैलिडेशन है तो हमने उसे 5 पार्ट्स में डिवाइड किया ना, और फिर वो हर पार्ट को डिफरेंटली, तो इन अ वे at some point all of our data was acting as a testing data, right? At some point हम ये कह सकते हैं because validation is a kind of testing. तो वो सारों के लिए अगर लेट्स से अगर वो डेटा पॉइंट अगर पहले से एग्जिस्ट ना करता हो हमारे ट्रेनिंग मॉडल में, तो वो सारे डेटा पॉइंट्स के लिए उसमें एक्यूरेटली प्लॉट करेगा। फिर इसका ये होता है।
So you are carrying out validation. You split data into 2 parts. Test data को भूल जाएंगे, right? So we do not have a test data, right? So you have train and validation data, right? So once you have hypothesis, using training data, that hypothesis need to be validated on the validation data. You evaluate loss on the validation data, and you pick the model for which the validation loss is minimized. इससे होगा क्या? इससे you will expect that your model would also work fine on the test data, right? Because it is working on validation data.
सर हम अगर लेट्स से ये 5 फोल्ड की जगह 6 फोल्ड वैलिडेशन हो या फिर लेट्स से 3 फोल्ड वैलिडेशन होती हमारी, तो उसके अंदर हमारे हम इसी साइज की वैलिडेशन सेट लेते या फिर हम पूरा जो हमारा ट्रेन सेट है उसको 3 में डिवाइड करते, हमारा वैलिडेशन का वो साइज बढ़ जाता है डेटा सेट का। लाइक वैलिडेशन में जरूरी है कि हम ट्रेन डेटा में सारी वैल्यूज कवर करें, जिस तरह इसमें हमने बारी बारी जो 5 सेट्स लिए हैं उनमें हमारी ट्रेन डेटा सारे कवर हो गए। तो अगर हमारी 3 फोल्ड वैलिडेशन हो तो उसके अंदर भी हम सारी ट्रेन डेटा कवर करें,
Yes,
इस तरह होगा।
you take 3 parts, right? As the name suggests, it's a folding. You create folds of the data, right? So it's 5 folds.
Okay, thank you.
You will get 3 parts. Yes. ठीक है जी। Okay. So there's we have time, right? What's time? Okay, probably we stop here. There's one more topic, which is the formulation of this generalization. So we can cover it offline. So any questions for today's session?
सर मैं पूछना था कि जो हमारे नंबर ऑफ कैंडिडेट हाइपोथेसिस होते हैं उसको क्या चीज़ डिटरमिन करती है?
Nature of problem, your experience.
सही।
Primarily it's the nature of problem.
राइट। जितनी कॉम्प्लेक्स होगी उसके हिसाब से फिर आपको जो है डिफरेंट उसको मॉडल्स टेस्ट करने पड़ेंगे।
Usually guys in industry, so when I work with them, so they just run all the algorithms in parallel and just pick the one and that is working, that is giving the lowest error. They just don't bother. But yeah, but as we progress in the course, we will learn how to select the hyperparameters, how to tune parameters, and for so what are the algorithms that are suited for different types of problems.
यानी कि कुछ हाइपोथेसिस हैं जो कि सेट हैं जो कि करने ही करने हैं टेस्ट।
Yeah, obviously. So I think mostly, decision trees are good in some applications. If you have some prior knowledge about the distribution from which the data is drawn. So based on those priors, we can reduce the size of hypothesis class.
Sir, I had a question. तो अभी जो हमने स्टॉक वाला जो एग्जांपल किया था तो उसके apart from regression, what other hypotheses could we use?
Decision tree.
Oh, okay.
Yeah, decision forest, boosted decision tree. Yeah, these are all used for regression. You can use neural network. This is a simple mathematical function. Okay, sure. Any other questions?
Sir. सर अगर जो स्टेप एस्टिमेशन या क्या लें स्टेप प्रेडिक्शन वाली प्रॉब्लम को हमने रिग्रेशन के बजाय क्लासिफिकेशन की तरह ट्रीट करना हो तो could we say that if the prediction of the steps or if the output of the problem falls in a set of known steps तो वो मल्टी क्लास क्लासिफिकेशन प्रॉब्लम बन जाती है
But that won't be an intelligent way to do it. You can treat it regression and you can round it to the nearest integer.
Right, sir. सिर्फ वो ambiguity दूर करने के लिए.
बिल्कुल ठीक है. Yeah, but I would prefer to solve it as a regression and you can round it. Or you can floor or you can seal to the nearest integer if you want a complete step. Yeah. Any other questions? Any feedback?
Sir. सर अमूमन हैंड रेज करने का वो मिस हो जाता है अमूमन आपसे यानी कि I'm torn between writing it in the chat box or asking it by unmuting myself because whenever I've raised the hand, sometimes you missed it.
My apologies. I will take care of it. Yeah,
right,
because there are it's too much ongoing. Yeah, but I will take care of it, inshallah. My apologies. Yeah, but
sir, Friday sessions question answer होंगे या फिर like tutorials होंगे proper like question solving वगैरह?
Currently, I have planned that I will review the material that is covered in the pre-recorded modules. In addition to that, I will also solve some problems, and I will also review the material on LA and probability. इस तरह कुछ कर रहे होंगे.
ठीक है और सर हमारी जो आपने कहा था कि हमारी सॉरी हमारे क्विज़ेस किस वीक से शुरू हो रहे हैं?
नेक्स्ट वीक से जी.
ओके सर.
So some students have requested to shift the quiz and sessions to Wednesday from Friday. We will be conducting a poll over the weekend. I am fine either way, but I'm more inclined towards keeping it on Friday because we have at least 2 students who have 15-minute clash with the Wednesday session. Yeah. So, but yeah, we will launch a poll and then we can decide whether we want to keep it on Wednesday and Friday. Wednesday को तो फिर Wednesday में quiz होगा फिर आपका. Okay, we stop here and then if there are no more questions.
हाँ सर एक चीज़ थी कि अगर आप फॉर एग्जांपल वो पॉइंट कर रहे होते हैं किसी स्लाइड के ऊपर तो मेरे ख्याल से आपका जो कर्सर है माउस का वो विजिबल नहीं हो रहा होता तो
Yeah, I have most likely next time से ना I'm not comfortable with I'm comfortable but I don't want to use slides so I will be using I'll be writing, I'll be solving the problems. तो सब कुछ visible होगा आपका. Will go slow.
Because
And thank you for comment. मैं note किया इस बात को. And I will resolve this. Okay. ठीक है जी. So we stop here. See you next week inshallah. Stay safe.
inshallah.